Welcome to the Problems Channel Season 3, Episode 34, the episode which I titled Hyperbolic Functions Defined by Direct Analogy with Trigonometric Functions, because in this episode we will unravel the mystery of why hyperbolic functions are called hyperbolic and what does a hyperbola have to do with it to begin with. But before we deep dive into the underlying mathematics, as a traditional and friendly reminder, if you're joining our channel mid-season, then first of all, thank you very much for your vote of confidence. Thank you for subscribing to our channel and welcome to our channel. And second of all, perhaps the most efficient way for you to gain the most academic benefit from working with the material that we present on this channel is for you to go to the homepage of our channel, and at the top of that page, in the channel's trailer section, find the episode titled The Problems Channel How To. We recommend that you watch that episode in its entirety, follow all the instructions that we give in that episode, because in that episode we explain and motivate everything that we do on this channel. If you have any questions, then by all means do ask. The best way to ask your question is to find an episode on the channel that is of interest to you and use the comment section under that episode, and I will take it from there. And of course, and as usual, I would like to extend my deepest gratitude to all the current subscribers and the current supporters of our channel. The objective of the mathematical problem S3E34 was to show that the four hyperbolic functions, the hyperbolic cosine, the hyperbolic sine, the hyperbolic tangent, and the hyperbolic cotangent, can be defined by a direct analogy with their circular cousins, the trigonometric functions of cosine, sine, tangent, and cotangent, provided that these trigonometric functions are defined via the origin-centered unit circle. If you want to solve this problem on your own still, then we suggest that at this point you walk away from our presentation and try to do the needful on your own. But if you need a hint, I have the following three hints for you. One way to solve the mathematical problem S3E34 is to begin with the classical definition of the four popular circular functions using the origin-centered unit circle shown on the left side of your screen over here. The second hint is the following: what is the length of the radius of the origin-centered unit circle? And the third and the final hint is the following: if the length of the radius of the origin-centered unit circle is what it is, then what one tactically advantageous interpretation of the angle theta, that is the argument to all four trigonometric functions at hand, is. In order to show that the four hyperbolic functions of cosine, sine, tangent, and cotangent can be defined by a direct analogy with their circular cousins, the trigonometric functions of cosine, sine, tangent, and tangent, which are defined using the origin-center unit circle, we need to establish a certain amount of tactically actionable material that we can parallel translate later on from one setting into another, and we construct this material as follows. As yet another hint, we will suggestively stop using the origin-center unit circle as the words origin-centered unit circle, and we will start suggestively using the words generating curve, a generating curve G. As such, let a generating curve G be the origin-center unit circle shown in yellow on the left side of your screen, where we construct that generating curve using the traditional Cartesian coordinate system, in which the axis, the x-axis shown on the bottom and the y-axis shown on the left, are perpendicular or orthogonal with respect to each other, the name of the origin is the traditional uppercase O. And under these conditions, we will agree that the curve G intersects the positive branch of the x-axis at the point A, uppercase A, which has the coordinates 1, 0, and that the generating curve G intersects the positive branch of the y-axis at the point U that has the coordinates 0 and 1. And then we pick a point P with the coordinates x, y at random on the generating curve G in the first quadrant, which is to say that the angle that is formed by the positive branch of the real axis and the radius OP extended, to which we will refer as theta, the angle AOP is strictly less than pi over 2 radians. We measure the angle theta in radians and is greater than 0. Then under these conditions, using our generating curve, the four circular functions of cosine, sine, tangent, and cotangent can be defined as follows. A geometric equivalent of the circular function of cosine of the central angle theta will be what? Well, if we project the point P orthogonally onto the positive branch of the x-axis into the point B that has the coordinates x and 0, then the geometric or ageometric equivalent of the trigonometric function of cosine evaluated at the argument that is the central angle theta formed by the point P on the generating curve G will be the line segment OB, and more precisely the length of the line segment OB. As such, we will say that the geometric equivalent of the cosine of the angle theta will be the length of the line segment OB. Likewise, the geometric equivalent or ageometric equivalent of the trigonometric function of sine will be the line segment PB, or more technically correctly, it will be the length of the line segment PB, or the distance between the points P and the point B. As such, we will say that the geometric or ageometric equivalent of the trigonometric function of sine evaluated at the argument theta will be the length of the line segment PB. And lastly, we need to cover the remaining two trigonometric or circular functions of tangent and cotangent, and we can do it in a straightforward manner. That is, for the generating curve G, shown over here, we construct a tangent through the point where that curve intersects the positive branch of the x-axis through the point A, that is this tangent right here. And where that tangent intersects the extended radius OP, we mark that spot as a point, and we name it uppercase C. Then, by its popular definition, a trigonometric equivalent of the trigonometric function of tangent evaluated at the argument theta, that is the central angle, then will be what? Well, technically it is a ratio between the length of the opposite side to the length of the adjacent side. So, but the adjacent side will be what? The adjacent side is the line segment OA, and the length of the line segment OA, let's write it down over here, the length of the line segment OA is 1. This is how we constructed our generating curve. As such, a geometric equivalent of the trigonometric function of tangent will be the ratio of the length of the line segment, let's say CA, to the length of the line segment OA, but this is CA over 1, and this will be the line segment CA. And finally, for the trigonometric function of cotangent, we come up with a similar geometric interpretation, but this time we will need to make an intermediate step and recall the theorem from, let's say, Euclid's Elements, book number 1, where Euclid proves that if we have two parallel straight lines, and here such two parallel straight lines are the x-axis and another tangent to the generating curve G, but this time through the point where that generating curve intersects the positive branch of the y-axis through the point U. This tangent is shown right here, until that tangent intersects the radius OP extended. And in this case, that means that the magnitude of this here angle right here will also be theta, because we have a straight line DU. See, DU right here. Maybe I can even show you better this way. The straight line DO, the straight line DO, falling on two parallel straight lines, the x-axis and the tangent UD. And that means that the magnitude of the angle UDO will be equal to the magnitude of the angle AOD. And by its popular definition, then the value of the trigonometric function of cotangent evaluated at the angle theta will be what? Will be the ratio of the size of the length of the adjacent side. So it will be the length of the line segment UD divided by the length of the opposite side, and that will be the side OU, but the distance OU is equal to 1. So here we will say also the distance OU is also 1. The distance from the point O to the point A is 1, and the distance from the point O to the point U is 1. This is how we constructed these points. Consequently, a geometric interpretation of the trigonometric function of cotangent evaluated at the angle theta will be the length of the line segment UD. And now that we carried out the construction of the basic material of the fodder that we will parallel translate from one setting to another, here is the time for the hint that I provided earlier. While this problem is not too easy, it is also not too difficult, and it should be within the grasp of a motivated upper high school student or a freshman in college, provided that that student makes the following key observation. Using the methods of basic integral calculus, it can be shown that the length of the arc, shown in red over here on the right side of your screen, of a circle or radius r spanned by the central angle theta, which is measured in radians, is equal to the product of the length of the radius and the magnitude of that central angle. And likewise, by using the methods of basic integral calculus, it can be shown that the area of the corresponding circular sector that is spanned by the central angle theta on the circle of radius r is given by half product of the square of the length of the radius and the magnitude of that central angle. And going back to my second hint, in this case, behind the generating curve, we have the origin-centered unit circle, and that means that the length of the radius of the circle is what? The length of the radius of the circle is 1. That was my hint number 2. And what is the hint number 2? Well, the hint number 3. The hint number 3, if the length of the radius of our circle is 1, substituting it into this formula and into this formula, we obtain the following results. The arc length in this case of the corresponding circle will be also represented by the magnitude of the central angle theta, provided that this angle measured in radians. And more importantly, the area of the corresponding circular sector is given by 1/2 of the magnitude of the central angle, provided that the angle is measured in radians. If we multiply both sides of this relation by 2, times 2 times 2, cancel, we obtain this relation shown over here on the right bottom of your screen. Theta is twice the area of the corresponding circular sector. And that was my hint number 3. In other words, usually and traditionally in all the textbooks, the argument to the 4 circular functions, cosine, sine, tangent, and cotangent, is what? Is a planar angle, theta. But if we want to, we can and we may reinterpret the meaning of this argument or of that parameter as twice the area of the corresponding circular sector that was spanned by this central angle. And now we want to conduct the following experiment. If we take this idea and parallel translate it into the setting where behind the generating curve there sits not the origin center unit circle, but the origin center unit hyperbola, then what advantageous material can we excavate? In other words, in this case, if we take that the argument to our future hyperbolic functions or future functions that we do not know what to call, let's pretend this is a miniature mock discovery, what will be the shape of the functions x and y that capture our circular functions, but the analog of the circular functions in the case of a hyperbola as a generating curve, b. Wonderful. We now do three things. First, we replace our generating curve that used to be in the previous segment, the origin center unit circle, with the origin center unit hyperbola. Thing number two, we carry all the material that we generated in the previous segment verbatim into the new setting. And number three, we take our idea that we generated in the previous segment and put it into action. That is, we now will treat the argument or the parameter to the functions that we are about to call hyperbolic and the functions whose shape we're about to discover as not the planar angle as it used to be with the circular functions, but we treat the hyperbolic angle as twice the area of the corresponding hyperbolic sector, or as you saw just a second ago, the hyperbolic pizza. And how is the hyperbolic pizza or the hyperbolic sector formed? Well, our generating curve G is now the origin center unit hyperbola, and that means that the canonical equation of such a curve in the traditional Cartesian coordinate system is shown over here. X squared minus y squared equals 1. And again, because remember the step number one that we are doing in this stage of our solution is we carry out all the material from the previous setting into the new setting. We have our x-axis, we have our y-axis, they are orthogonal, they intersect at the origin, which we call O, and in this Cartesian coordinate system, the canonical equation of the origin center unit hyperbola is shown over here. X squared minus y squared equals to 1. We now bring in exactly the same lettering of all the material that we generated in the previous segment. That is, the place where our generating curve G intersects the positive branch of the x-axis is the point A with the coordinates 1, 0. This point is shown over here. The generating curve G is shown in yellow over here to the best of my ability. It goes like this, and in all fairness, the asymptotes for the origin center unit hyperbola is the other straight lines y equals plus minus x. So fairly quickly, the hyperbola over here, the branch that goes that way, gets very close to this y is equal to x straight line. But again, this is my by hand rendering of the corresponding branch of the origin center unit hyperbola. And this time our generating curve does not intersect the positive branch of the y-axis, but still, if we want, and we will actually do that in the extra for experts section, we can basically give a hint of the origin center unit circle in order to construct that point U with the coordinates 0 and 1. Here we still selected, I erase this material because it's no longer there, but we still pick the point U on the positive branch of the y-axis such that the coordinates of the point are 0 and 1. The components are shown over here. Then again, at random, we pick the point P on the generating curve, the random point P on the generating curve G with the coordinates xy in such a way that the angle AOP, this time, remember that the interpretation of the argument for our soon to be discovered functions is not the traditional angle, but twice the area of the hyperbolic sector. But this time, for definitiveness, we still say that the magnitude of the angle AOP is strictly less than pi over 2, strictly larger than 0. That is to say that the point P is picked in the first quadrant. And then we do exactly the same steps that to this material as we carried out in the previous setting. We project the point P orthogonally onto the y-axis into the point B that has the coordinates x, 0. That is exactly what we did with the circular functions. Then we construct a tangent to the generating curve G through the point where that curve intersects the positive branch of the x-axis. Here is this tangent, until this tangent intersects the radius of the point P, or the line segment OP, at the point C. And one more step, setting things up for the hyperbolic cotangent. We draw not a tangent, but this time a straight line that is orthogonal to the portion of the positive branch of the y-axis through the point U, orthogonal to the y-axis through the point U, until this orthogonal straight line intersects the radius OP at the point D. And now we can understand how this area to which we refer as the hyperbolic sector is formed. The hyperbolic sector is a planar region that is trapped between three geometric objects. It is trapped below the radius OP. It is trapped to the left, let's say logically, or towards the y-axis with respect to the bounding generating curve G, which is the origin center unit hyperbola, and above the positive branch of the x-axis. I hatched that hyperbolic sector with yellow lines. You can see it over here. So this is, we can say in some sense, this is a curvilinear triangle if you want to, but under a fairly tight artistic license, we still see the similarity between the hyperbolic sector and the circular sector, because remember, in case of the circular sector, we had what? We had the planar region trapped between two radii of the generating circle, with the exception, of course, that in the case of the origin center unit circle, the length of the radii are the same. But in case of the hyperbola, the lengths of the radii are no longer the same. The line segment OA is still a radius of the origin center unit hyperbola, but its length evidently over here, let's put it as 1, and this distance is still 1 as captured over here. But the distance from the point O to the point P, which is also a radius of that hyperbola, evidently is distinct from 1. But now the main technical idea that, again, you were expected to generate on your own is the following. We will treat the twice the area of this here hyperbolic sector as the argument to our future functions that we're about to discover, in which we will call hyperbolic. And that idea brings us to the following. Wonderful. In order to extract the actionable mathematics from the idea that we generated just now, we step as follows. I went this way, so let's say this way. Notice that the area of the hyperbolic sector, whose construction I just explained a few seconds ago, can be represented as follows. So we will refer to the argument of our future soon to be discovered functions, which we will soon call hyperbolic for the reasons that we will understand as the solution of our problem unfolds, as t. And we know that this is twice the, I'll use the fancy a, twice the area of the corresponding hyperbolic sector. So let's say this right here is a. So this area right here is fancy a. So how can we compute that area? Observe that that area can be represented as, take a look, this is a small puzzle for you. What would you do over here, and how would you unwind this situation? What would be your next step in this case? Well, the area of the hyperbolic sector in question can be represented as the difference this time between the area of the right by construction triangle PBO and what? And the area trapped under the corresponding portion of our generating curve G. And that area spans from the point A with the coordinates 1, 0. So along the x-axis will be 1 to what? What is the coordinate of the point B? The orthogonal projection of a sample point B that sits on our generating curve. X. Exactly. So this is what we write over here. So the area in question is equal to the difference between the area of the triangle, which one? PBO, minus the area of the curvilinear planar region called again what? PBA. Let's write it down. PBA. Now, look at this. The area of the triangle PBO is what? In terms of the locally available material? Well, it's 1/2 of x times y. So this is equal to 1/2 of x times y. I want to make sure that all the students in the audience understand this. The orthogonal projection of the point P with the coordinates x, y picked at random on the generating curve G in such a way that the corresponding angle is acute is what? Is the point B with the coordinates x and 0. So this distance over here is x from the origin, and the vertical displacement of that point with respect to the positive branch of the x-axis is what? This is y. Consequently, half the distance, half the length of the base times the length of the height. This is our area of the triangle PBO. Middle school, wonderful. Now comes the not so middle school material. How do we represent the area of the planar region PBA? Well, this is a definite integral, exactly. And how does the integral run from 1 to x, from 1 to x over what? Well, remember this. This is our canonical representation or canonical equation of the generating curve in the chosen Cartesian, in the chosen coordinate system. So what do we take? We take the positive branch of whatever remains for y dx. And now it should become evident why did I spend that much time and why did I put the episode, season 3 episode 32 together, where we solved the mathematical problem S3E34, because there we evaluated precisely this integral, except that instead of 1 we had the parameter a. So now I will not be dwelling too much on the computation of this integral. I will capitalize on the fact that we did all this heavy lifting in season 3 episode 32. The link in the comment section to this episode. I recommend that you watch that episode, and in some sense these two episodes, the season 3 episode 32 and this episode, season 3 episode 34, make up a miniature 2-episode series that is dedicated precisely to the idea that the 4 popular hyperbolic functions can be defined by a direct analogy with their circular cousins, provided that the circular cousins are defined using the mechanism to which we refer as the unit-centered, origin-centered unit circle. But in case you need some guidance and you do not want to watch this episode, here is how this integral can be evaluated. There were 2 main reasons why I put the season 3 episode 32 together. First of all, to show, in the words of the famous mathematician Michael Atiyah, that the devil will take your soul, because unfortunately most students of mathematics shuffle symbols and manipulate the underlying algebra of things without really understanding the meaning of the symbols that they shuffle. That was the reason number 1. And reason number 2 is to show you that the integral that we are about to evaluate in this particular case, square root of x squared minus a squared, can be evaluated without the famous, or what is now called, hyperbolic substitutions, but using the substitutions known as the Eulerian substitutions, named so after the Swiss-born mathematician Leonhard Euler, who introduced these substitutions and whose main idea I explained precisely in season 3 episode 32. And the wonderful thing about, well, awesomely talented people, of course, of which Leonhard Euler was, is that when they do things, they pave the way for new things to happen. And precisely the Eulerian substitutions, they paved the way for the discovery, or a mock discovery in our case, the so-called hyperbolic functions and the substitutions that we use in order to evaluate this here integral, square root of x squared minus a squared, where a is equal to 1, are the we can say linear substitutions, and we will see it in a second over here. So this integral, again, I evaluated in great detail in this episode over here under the guise of this problem, S3E34. There are two different ways to do it. We can right away unwind the integrand with one direct Eulerian substitution, or we can take a slightly more scenic route. We don't have to, but we may, and do the following. We designate the square root as t minus x, t being the new variable of integration. Do not confuse it with this one. This is just traditional substitution t over here. And if we do this substitution, then evidently right away, for the purposes of the reverse substitution, what is t? X plus the square root. Now, once we do this, we square both sides, we obtain this relation: x is equal to t squared plus 1 over 2t. The first differential is trivial. We can do it in our mind. It's t squared minus 1 over 2t squared. And then the square root of x squared minus 1 in this case is what? Well, we know t, we know x. From t we subtract this, 2t times t, 2t squared minus t squared minus 1. There you have it, t squared minus 1 over 2t. Once we put all this material, the first differential dx, and 1 divided by this, we will obtain basically everything cancels out and we have only 1. But where did this integral come from? Well, we integrate this, we apply the integration by parts to this here integral. We're taking the square root as ux is v, so u times v becomes this product over here, evaluated from the boundaries of 1 to x. At the lower boundary, when x is 1, this product vanishes. At the upper boundary, it is this guy. But x squared minus 1 square rooted is what? Remember, our point sits on the generating curve G, which is the origin-centered unit hyperbola. This equation is satisfied by the coordinates x, y. It means that the square root of x squared minus 1 is precisely what? Precisely y. This is what I entered for you over here, x times y. Minus, here we have minus what? X times the first differential of this guy. One copy of x will be generated by this differential, another copy of x here from v, x squared dx over square root. Here we execute the popular maneuver. We add 1, we subtract 1. When we subtract 1, we have the cancellation going, happy cancellation. The complete copy over square root gives us 1 square root, and this comes back to the original integral I. So we have minus I minus the term that has no variable of integration in the numerator, dx over square root of x squared minus 1. So we make I jump to the left hand side of the equal sign. So from here it follows twice the integral I is equal to product x times y minus the integral this guy. And this guy, I explain how we unwind. This is a substitution. This is x, first differential, square root. Once we put all this material into this integral, precisely because the square root sits in the denominator, we will have, look at this, t squared minus 1, t squared minus 1, cancel, cancel. And then we have 2t in the numerator, 2t squared in the denominator. 2's cancel out, t's cancel out, 1 copy of t survives, and from here we come to here. This is a trivial logarithm, integral, logarithm of absolute value of t plus a silly constant, but now we unwind it back into the original shape with the reverse substitution. From here, t is equal to x plus, but we know that this is x plus y, and here we have it log of x plus y. In case you are wondering where did the boundaries of integration go, well, they're still here. Look, apply them over here, unwind. Again, at the low boundary, look at what happens. X squared becomes 1, 1 minus 1, 0, square root of 0 is 0. 0 plus 1 is 1. The logarithm in base e of 1 is what? Is 0, gone. So whatever material left will be at the upper boundary over here from 1 to x. Only the material that is associated with the upper boundary of integration survives. and this will be exactly that shape, x plus square root of x squared minus 1, coming back to the canonical equation, generating curve, origin-centered, unit hyperbola, the logarithm of x plus y. All these computations should be transparent, and that is why I said this problem is not too easy, but it's not too difficult. It is within the grasp of a motivated upper high school students or a freshman in college. You can see all the manipulations are elementary. There is nothing horribly complicated going on over here, but this is the result that you were expected to obtain over here. And now we will come back and rewrite this integral, preparing it. Remember, we still have our area represented as what? As the difference between the areas of the right triangle PBO and the area trapped under the curve of our generating branch PBA. Very well, we now take this result and write down the expression for the integral I, shown over here from 1 to x of square root of x squared minus 1 over dx as what? 1/2 of the product xy minus 1/2 of the logarithm in base e of x plus y. I put this expression over here, and remember our area represented as the difference. So from this area we subtract the area trapped under the corresponding branch of the generating curve. Once we open up the parentheses, what do we see? We see that 1/2 of the product xy and the other 1/2 of the product xy cancel each other out. This and this is gone. Minus times minus becomes a plus, and we have what? We have 1/2 of the logarithm in base e of the sum x plus y. Again, do not be confused by the fact that I here use the symbol y, because why? We do it because our point P sets on the generating curve G, the origin center unit hyperbola. It satisfies this canonical expression, a canonical equation, and consequently the square root of x squared plus 1 corresponds to the positive branch that lives in the upper half plane or above the positive branch of the x-axis. This is all there is to it. And now we go back to our representation or interpretation of the argument of the future functions that we're about to discover in our mock discovery hyperbolic. The argument of these functions will be twice the area of the corresponding hyperbolic sector, which we just evaluated to be this here number. Consequently, we now go back to this, and from here it follows that our argument t is equal to logarithm in base e of x plus y. All these manipulations should be transparent, very straightforward. You should be able to carry them out on your own. Now we potentialize both sides of this expression, and from here it follows what? From here it follows that e raised to the power t is equal to x plus y. And now once we have this result on the books, you see how naturally it emerges. But it is important to realize, and that is why I took the pains to do the right thing in season 3 episode 32 while we were solving the mathematical problem S3E34 and show that for a clean deduction that does not involve any circular reasoning at all, we need to have the substitutions that are different from the hyperbolic substitutions. Remember, when we're trying to discover something, it means that we do not know it yet. And in our current manipulations, we cannot use that very material that we're about to discover. And that was the experiment in showing you how this can be done. But now that we have this result on the books, what would be your next maneuver? What would you do next? Well, I would go back to our canonical equation of the generating curve and write it down as follows: x minus y times x plus y is equal to 1. As a matter of fact, I think I used this factorization in the episode, in season 3, episode 32, but there I used slightly different substitution also to come out victorious. So here the difference x minus y will be 1 divided by x plus y. You see, this is middle school algebra, but now we have this expression, this expression, this expression. What does it mean? It means that e is raised to the power minus t, e raised to the power minus t. Look at this. See, e. So now that we have two relations, one for the sum and one for the difference, what do? First, we subtract the second relation from the first one, and by so doing, we wipe out the y component of the coordinate of our sample point P on the generating curve and obtain two copies of x. As such, for x as a function of t of our new parameter, we have 1/2 of the sum e raised to the power of t and e raised to the power minus t. And what does that mean? Remember that x is the first component of the point B, which is the orthogonal projection of the point B on a generating curve G onto the positive branch of the y of the x-axis. And what does that mean? That means that this is now the function to which we refer as cosine h, or hyperbolic cosine of the argument t, and its geometric interpretation, or a geometric interpretation, is precisely the length of the line segment OB. And this is precisely a direct analogy of how the corresponding circular function was interpreted or defined using the origin-centered unit circle. Now, next, if we subtract the second relation from the first one, then we will wipe out the x component and thus generate two copies of the y component. Consequently, for y as a function of t, we will have 1/2 of the difference of e, the base of the natural logarithm, raised to the power t, minus e raised to the power minus t. And what does that mean? Well, now the y component is this distance right here, is the y component of the sample point P on the corresponding branch of the generating curve G. And that means what? This is how we define the hyperbolic sine h of t, and a geometric interpretation of that new invented or discovered function, if you will, the hyperbolic function, is the length of the line segment P B, again, by a direct analogy with how the corresponding circular functions are defined in accordance with the declared or announced title of this episode, Hyperbolic Functions, by a direct analogy with the circular functions. And what is left to do? Well, the only thing that's left to do is for us to define the hyperbolic tangent and cotangent. That is, once we have this result on the books, let's separate it. So far we have deduced our material up to here, and now we go back to the geometry of the underlying material, and what do we see? We see that the triangle OAC is right by construction, the triangle OBP is right by construction, and you should be able to educate me on the matters of why these two right triangles are similar. And because they're similar, by Euclid's Elements, book 6, proposition 4, the lengths of the sides lying opposite equal angles are in the same proportion, where the corresponding sides lie opposite equal angles, on and on and on. So now we construct the following proportion: the length of the side OC, the opposite side to this angle over here. But we need to be careful. Remember, our argument to the hyperbolic functions now is what? It's not the angle, not the planar angle, as it is the case with the circular functions, but now the area, twice the area of the corresponding hyperbolic sector, the hyperbolic pizza. So now that is the argument. So, but we go back to the Euclidean geometry, we still use planar angles. So in this case, the length of the opposite side relates to the length of the adjacent side, OC to OA, which is what? OA is 1. Remember, OA is 1. So the length of the side OC, in this case numerically, is this in the same proportion as what? The length of the side PB to the length of the side BO or OB. But this is how we already defined the hyperbolic sine, hyperbolic cosine. This is a new function. We just discovered it. Wonderful. We call it the hyperbolic tangent. Tangent H, the same argument, the same parameter T. So this is our result over here. Let's see if I can highlight it for you so that you can see it easily. This is the result. So geometrically, this new hyperbolic function corresponds to the length of the line segment AC. If you go back to our previous segments, you will see that precisely that is how, through the tangent to the generating curve at the point where the curve intersects the positive branch of the x-axis, we had what? We had the circular equivalent of this, the trigonometric tangent or the circular tangent. And by the same exact maneuver, we discovered the fourth function in our bunch, the hyperbolic cotangent, but this time we go with which triangles? You guys tell me real quick. The triangles should be OUB, the right triangle OUD, and the right triangle OBP. But this time, this angle is equal to this angle, and instead of taking the ratio of the opposite to adjacent, we take adjacent to the opposite. And what do I have? UD divided by OU. OU is 1, so UD is what? Is the cotangent. Bam, a geometric interpretation of our analytical, algebraic, or however you want to define this object. And that is shown over here. So this is the result that we obtained, again, purely geometrically. And I hope that I held up my end of the bargain, where I announced the title of this episode to be Hyperbolic Functions Defined by a Direct Analogy with Their Circular Cousins. This is how it's done. Absolutely wonderful. And in some sense, at this point, the algebra can take over. And what can we do? Well, right away, without actually, you see, this goes back to what I said in season 3, episode 32, Michael Atiyah. The devil will take your soul. Once we switch to algebra, we stop thinking about the meaning and mind-numbing symbolic shuffling without any second thought to it. But with this simple symbolic shuffling exercise, what can we show? Well, the square of the hyperbolic cosine subtracted from the square of the hyperbolic sine will produce the positive unity. This can be done, and from that point onward, once we have all four usual suspects locked in, again, in the purely algebraic manner, we can develop the rest of the theory of hyperbolic functions from that point onward without looking back at the underlying geometry, even though the geometry will help. And now I'll tell you in a second why. Now, for example, the popular functions or the identities, which are the equivalents of the identities that exist for circular functions. For example, the trigonometric or circular sine of x plus y, or circular cosine of x plus y is what? Expressed somehow as a sum of products of the sine and cosine of the individual arguments. These formulas can also be deduced in the hyperbolic case purely, again, algebraically. Simply start multiplying this function by this function, and then this by the function of the same different argument. Here the same thing, different argument. Sum, subtract, multiply by 2, divide by 2, arrange the whole thing. Yes, it can be done, no problem, through raw algebraic manipulation. But this, for example, identities for the sine and cosine in the hyperbolic case, hyperbolic cosine and hyperbolic sine of the argument, for example, t plus u, another one for sum, can also be deduced purely geometrically, but this requires a little bit extra effort, and this is not the point. This is not the point of this exercise. The point of this exercise was my desire to show that the hyperbolic functions can be defined by a direct analogy with their circular cousins, and this is how it is done. In most textbooks, it is never done that way. So here you now saw the very transparent and straightforward underlying geometry of the justification of why the word hyperbolic makes it into the names of these functions. Why hyperbolic functions I called hyperbolic in the first place. What does the hyperbola have to do with these functions? Well, now we know this is what it has to do with the origin-centered unit hyperbola by direct analogy with the origin-centered unit circle. Coming back to this circle will make its encore appearance one more time in a few seconds in the Extra for Experts episode. If you're interested, stay tuned. If not, you can skip to the next challenge. But Here is the thing. If you go back to our circular representation and circular definition of circular functions, you will see that it is tempting to say that the reciprocal functions, one divided by the cosine and one divided by the sine, in terms of circular functions, can be defined by the corresponding geometry, but this geometry will fail. In this case, for example, the line segment OC is definitely not the reciprocal of the hyperbolic, or was it OD, hyperbolic cosine, and not the corresponding line segment OD. OC, we need to think which one is definitely not the reciprocal of the hyperbolic sine. So this direct analogy will not work. But the other analogy that I'm about to explain will work, and I will cover this analogy in the Extra for Experts segment. That is, stepping back into the world of circular functions for a moment, take our favorite origin-centered unit circle shown in white partially on the left side of your screen. In this case, it is definitely the case that the length of the line segment OC, if this AC is a tangent to the circle at the point A, will be what? That will be a geometric interpretation of the reciprocal of the circular cosine, 1 divided by cosine. Why is that? Well, look at this again. We drop the point where the origin center unit circle intersects with this straight line AC with the radius of the point, let's say, picked on the origin center unit circle will be what? The length of the OC, the hypotenuse divided by the length of the adjacent side will be 1. And here it will be, again, the length of the hypotenuse, which will be 1, divided by the length of the adjacent side. And what's the adjacent side? The geometric equivalent of cosine, so 1 over cosine. Likewise, OD, the line segment OD that sits on this radius that runs through our point, will be a geometric interpretation of 1 over sine. Here, evidently, again, it will be a different angle, and you can unwind it from here. But this analogy breaks down in the land of hyperbolic functions. In other words, the line segment OC is definitely not a geometric interpretation of 1 divided by hyperbolic cosine. So how do we find it? Well, back in the day, I remember when I was attending my college preparation school, when I was in high school, our teacher also brought it down to this point. When I came home, I started thinking about it. This relation, geometric relation over the circular functions, breaks in the land of hyperbolic functions. How can we fix it? Well, here is the thing. On this channel, we put together already a course called Inversive Geometry, and in that course is based on my book, Inversive Geometry for All. In that book, chapter 3, problems 1 and 3, you will find it. And in the course itself, you will find this course under the courses tab at the home page of this channel. It is in episode 3, lecture 3. What we do is we use the so-called inversion of the plane with respect to a circle. These inversions come with 2 flavors, positive power and negative power. In this case, the positive power is enough. So what I did is this. I took the point B. In general, this point B will be located where outside of the origin center unit circle, because of course the point B can jump onto the parabola at point A, but this is the limiting or degenerate case, if you will. In general, when the point P is distinct from that point, the point B, the corresponding projection, will be located where outside, strictly outside of the origin center unit circle. And as the point B moves towards the point A, so will the point B, and here they will coincide. But inversion of the plane with respect to a circle with positive power leaves the points on the circle fixed, doesn't move them. The same inversion with negative power swaps them with diametrically opposite in general, but in our case, the point B will be located strictly outside of the origin center unit circle. We take that circle to be the circle of inversion. So in order to construct the reciprocal, the geometric image of the reciprocal of the hyperbolic cosine, what do we do? Well, we simply reflect the point B in the origin center unit circle. Game over. So one way to do it is to construct one tangent to the origin centered unit circle through the point B. that will be the line segment TB or BT shown in red over here, and then drop the perpendicular through T to the positive branch of the x-axis. This is it. That is why I told you for the reference you can either go read the book, chapter number 3, problem 1, problem 3. We solve both cases in these two problems when the point is located inside of the circle of inversion and outside. And in the course, it's episode 3, lecture 3. You can find all the Euclidean tools only solution of this problem. So all this beautiful stuff can be carried out again to boot with Euclidean tools alone, a straight edge and a compass. So a tangent through the point B, which is the orthogonal projection of the point B on the generating curve, the origin center unit hyperbola, and through that point perpendicular to the positive branch of the x-axis into the point F. So now we have it. The distance OF, or the line segment OF, or its length, is a geometric equivalent of the reciprocal of the hyperbolic cosine. Hyperbolic cosine. This is important to understand. You can prove this using the good old middle school plain Euclidean geometry, because all the triangles over here will be, this triangle is right, this triangle is right, they share the sides, hypotenuse, yada yada, similar triangles. You can prove it. Basically, the workhorse of the inversion of the plane with respect to a circle of radius r is what? The product of this distance times distance is r squared. But in our case, r is what? Again, 1. So there you go. If this is our original distance, this is its reciprocal. So the line segment OF represents the reciprocal of the hyperbolic cosine, which is 1 over x. Now the triangle OFT is what? Is right, and the line segment OT over here is a hypotenuse of length 1. So for the length of the side TF, what do we have? Well, it's the square root minus of 1 minus OF squared. So this distance squared, OF squared, right? This distance is square root of 1 squared minus OF squared, exactly. But OF is 1 over x, so this is the expression that we have. And now we go back to our definition of the hyperbolic tangent. You see the line segment AC. What was it? Well, it was the ratio of y to x. Y to x, and because the point y belongs to the unit hyperbola, it means that y is representable like so. Move the x in under the square root and obtain the same exact expression. You see, this is equal to this right here. This and this are the same thing, and that means that lengthwise, we have the length of the line segment TF is equal to the length of the line segment AC. And by construction, they're what? They're parallel. There we go. Now we go back to our point T, and once we connect it with the origin of the coordinate system, what do we get? We get the radius of length 1. But now we also lock in the angle. You see the angle FOT. FOT, I marked it gamma, and in the theory of hyperbolic functions, this angle carries its own dedicated name. It's called the hyperbolic amplitude, the hyperbolic amplitude of the point P on the corresponding origin center unit hyperbola, or it's called the Gudermannian. And the situation over here with this angle is somewhat a little bit involved, because two people were involved in its discovery or its introduction into mathematics. These were these two guys, two gentlemen, Johann Lambert, who lived in the years 1728 and 1777. He did his work on this matter in 1760, more than 200 years ago. And then also the gentleman by the name Christoph Gudermann. He lived between the years of 1798 and 1852, and he did his work in the year of 1830. So now, one more time, this now, switching back, see, we need to be careful over here. Area of the planar region, or twice the area of the corresponding hyperbolic sector. Good old Euclidean angle, and that is the connection between the circular functions and the hyperbolic functions. And this is exactly how we derive it. Again, not too complicated. It's all, roughly speaking, upper, let's say, middle school material, not more involved than that. But here we understand that the angle gamma over here is the good old planar Euclidean angle. And how do we obtain that angle? Again, tangent through the projection of the point P onto the x-axis to the unit origin, to the origin center unit circle, and then that point T already locks in the location of the formation of that angle. Let's say the angle, let's say AOT, if you will, is gamma. The hyperbolic amplitude, or the Gudermannian of the point P on the origin center unit hyperbola. And now we have, look at this, because this line segment also doubles up. Again, this goes back to the way the circular functions are defined. What is the length of the line segment? Radius times the circular cosine, not the hyperbolic cosine, but circular cosine. Right here, we drop 1, and there we have it. This is our connection. This is how we derive a connection between the circular cosine and the hyperbolic cosine. Awesome, we now know one geometric argument that in a clear fashion connects a circular cosine to its hyperbolic counterpart, and now let's do the same thing for the circular sine, tangent, and cotangent. And to that end, we go back to our canonical equation of the origin-centered unit hyperbola, x squared minus y squared equals 1, and we move the square of the y component to the right-hand side of the equal sign, and we obtain x squared equals 1 squared plus y squared. Now the question is, this is an algebraic relation, so what is a plausible geometric equivalent of this algebraic relationship? Well, the Pythagorean theorem comes to mind. Again, there is nothing more complicated over here than the good old middle school parallel translation. In order to manufacture a geometric equivalent of this algebraic relation, all we do is we take our logically vertical line segment PB, and we parallel translate it until it jumps and coincides with the tangent to the curve G at the point A over here, the tangent AC. In other words, we can say that the point K over here is the image of the point P under the parallel translation of that line segment, or we can say we basically project the point P onto the positive branch of the y-axis orthogonally, and as we do so, that straight line runs into this tangent, and boom, at their intersection we have the point K. In other words, the line segment PB is parallel to the line segment KA or AK, and they have equal length by construction. So now what do we do? Well, if the line segment KA is orthogonal to the positive branch of the x-axis, we have the triangle OAK that must be right. And in this case, again, the Pythagorean theorem is applicable to it. So for the square of the length of this hypotenuse, OK, we have OA squared plus AK squared. But OA is 1, and AK, as we just proved, is y. See, this is the coordinate y. So we have 1 plus y squared, which is x squared. What does that mean? Well, that implies that the distance OK is equal to x. And this gives us another wonderful way to construct the point K with Euclidean tools alone. All we have to do over here is stick the needle of our compass into the origin, open up the compass to the distance from the origin to the point B, and swing an arc until it intersects the tangent to the generating curve G at the point A. Boom, we have our point K. Wonderful. So we have this result. Now, our goal is to show that another wonderful property of the origin center unit hyperbola is the fact that the points O, T, and K are, amazingly enough, collinear. It doesn't look so on my silly drawing, of course, but if you do everything nicely in the software, you will see that these points will be collinear, and this is how we prove it. One way to prove it is to compute basically what amounts to, in modern times, the magnitude of cosine of the Gudermannian or of the hyperbolic amplitude of the point P. In other words, we compute two quantities, two magnitudes separately, and then we compare the results, and look, voila, we have the results are the same. So the ratio of OF to OT is the same as OF to 1 or OF, but in the previous segment we showed that this is equal to 1 over x. This is our reciprocal of the distance x, which we obtained through inversion of the plane in the origin center unit circle with positive power once. Wonderful. Now we do the same thing for the ratio of OA to the distance OK. See, OA to OK, OA to AK. OA is 1, AK we just proved. OA to OK, sorry, OK. This is OK. We just proved that OK is X, so 1 over X. So now we have the identity 1 over X in one computation, 1 over X in the other computation. And that means that effectively, if these two ratios are the same, well, we can go back to elementary plane Euclidean geometry. There is a theorem which states that if the ratios about the angle of the same magnitude are the same, these triangles are similar. But here we're basically saying that the magnitude of the cosine of gamma of the angle gamma is the same, which means that the angle gamma is the same. So the angle FOT by magnitude, FOT by magnitude is equal to the magnitude of the angle AOK. But the points A and F are collinear. The point O, the origin, is shared. How can this be? Well, it can mean only one thing, that the points O, T, and K, points O to K, are collinear. This is what we prove. So the idea here is to compute two ratios separately and then juxtapose the results. They are the same. The corresponding angle is the same. The points are collinear. Wonderful. So now we go back to the line segment TF. And with respect to the origin-centered unit circle, that line segment, remember from our earlier segment in this episode, is a geometric equivalent of the circular sine of gamma, the hyperbolic amplitude or the Gudermannian. And what is it equal to? Well, we just proved that the length of the line segment TF is equal to the length of the line segment AC. And what does that mean? This line segment is a geometric interpretation of the hyperbolic tangent AC. And this is another geometric reasoning which establishes a connection between a circular function and its hyperbolic counterpart. And likewise, let's do the last piece over here, AK, the length of the line segment AK, which is equal to the length of the line segment PB. We know that in the circular functions land, when we deal with the origin-centered unit circle, that distance divided by 1 is what? Is the tangent of this angle. So the circular tangent of the angle gamma is equal to numerically what? This line segment, which is this line segment, which is y, which is what? Which is the hyperbolic sine. So now we have, through this relation, one more connection, which we establish purely geometrically, hopefully in an intuitive way, which connects the circular tangent with the hyperbolic sine. And all we have to do now is to establish a connection between the circular cotangent and its hyperbolic counterpart. And yes, I know what you're thinking just about now. Why is Roman doing this when we can just take this relation over here, flip it upside down, and voila, we have our relationship? Well, Roman is doing it because Roman gave you a few episodes ago the quote by the famous mathematician Michael Atiyah, which said that the moment we begin shuffling algebraic symbols purely algebraically, we stop thinking geometrically, we stop thinking about the meaning. That is why we want to find the meaning before we inevitably, in some sense, give our soul to the devil and forget about all this geometric stuff and just start shuffling symbols in a purely algebraic manner. So we have over here the following situation. Remember our tangent to the origin-centered unit circle through the point U on the positive branch of the y-axis with the coordinates 0 and 1. Yes, you remember it. So this tangent will now intersect the straight line OTK. Remember, we proved that the points OTK are collinear at the point W. I marked it over here in red. Hopefully you can see it once you carry out your constructions, and I recommend that you always shadow my constructions by yourself in your favorite software. I use GeoGebra for all these manipulations, but you will see that these points K, T, and O are nicely collinear. The point W will be over here. And what do we have now? We have two right triangles, O, U, W, and another triangle, O, A, K. So these two triangles, OUW and OAK, are similar. Why are they similar? Well, because again, remember all this heavy lifting with proving the points are collinear, they sit on one straight line, yada yada. We have thus one straight line following on two parallel straight lines. Again, your favorite Euclid elements, book one. The theorem, the alternate angles must be equal. So we have the angle gamma over here. So now we construct the relation as follows. The adjacent side, the side UW divided by the opposite side, adjacent divided by the opposite. And in the similar triangle, we do what? We do adjacent side to the opposite, adjacent, opposite. So we go OA over AK. This time, in the previous segment, I made a mistake over there, but now AK. So OA is 1, but AK, this distance is PB, this distance PB, so 1 over PB, this is 1 over Y, so this is 1 over hyperbolic sine. And what is the ratio of the adjacent to the opposite do in the world of circular functions? Well, in the world of circular functions, it generates the trigonometric function of cotangent. So there we go. Circular cotangent, that is how it relates to its hyperbolic cousin. This connection is now evident, and again, we can develop more connections, again, maybe geometrically, maybe purely symbolically, but my point is that when these relations are dropped onto students out of just thin blue air without any motivation of any kind, it makes some students frustrated because where did these relations come from? But now with a straightforward geometric argument, I hope that you understand that I held my end of the bargain by titling this episode as hyperbolic functions defined by direct analogy, by a direct analogy with the trigonometric functions. And you also see a straightforward and beautiful geometric reasoning which establishes a connection between the circular functions and their hyperbolic counterparts. Lastly, before we move on to our next challenge, a few closing thoughts on circular and hyperbolic functions. You may know about it or you may not. If you do not know about it now, you will learn about it eventually when you go to college. But one major discovery that you will make there is that any good old function can be defined in a multitude of different ways. Even here, look at this. We defined our circular functions using the origin-centered unit circle, and we tried to carry out the same experiment with the hyperbolic functions, but that is just one way to define these functions. The other way is to define these functions through the so-called differential equations. For example, the circular functions for sine and cosine satisfy this here differential equation. This is how the mathematicians will write it. The second derivative of a function plus the original function itself vanishes. And the hyperbolic equivalent will be the second derivative minus the function itself vanishes into 0. In physics, we will write it slightly differently. The second derivative designated with 2 dots plus omega squared 0x will be 0 again. And this is the circular case. And the hyperbolic case, there will be a difference between the second time derivative and the function itself. And the other way, yet a different way to define a function is, for example, through the so-called infinite series. This is, I give you a sample definition of the circular sign. The terms over here flip-flop. It's an alternating series from 0 to positive infinity. And this is the hyperbolic sign. This is how it defined, similar to the circular cousin, but this time the terms do not flip-flop. There is no -1 raised to the nth power. And coming back to our more tactically advantageous utility of hyperbolic functions, if you missed that episode, I highly recommend that you actually watch it. It's season 2, episode 54. In that episode, we solved the problem S2P2. That was the second problem in physics during the season 2, towards the end of the season, as you can judge by the number of the episode. I explained how the so-called mathematical equivalence worked, and in this particular episode, in this problem, we had a massless rigid rod rotating in the horizontal plane with the constant angular velocity, omega 0, and at certain point from the pivot point of the rod, there was fixed a small bead, and at some point the thread that was holding the bead to the axis of rotation was cut. The bead started sliding along this rigid rod, and the question was, without friction, the question was to find the separation time and the separation velocity of the bead from the rod, on and on. Bottom line, this came down to this equation over here. So in some sense, we can also define this function yet another way, as a mechanical definition. If this mechanical experiment happens, then this is the function that solves the underlying differential equation, and this is exactly the case. You will see that x over here will be a specific incarnation of the hyperbolic cosine. The velocity with respect to the rod will be the first derivative. That will be sine. The acceleration will be the first derivative of the first derivative, or the second derivative of the coordinate itself, yet another cosine, scaled, yada yada, so on. This is how we put these hyperbolic functions to a good use, and we will see these hyperbolic functions in action on this channel on and on again. Now, this is it for the mathematical problem S3M19, and we will move on to a new challenge next. Very good, befitting our last discussion. Our next challenge will be the problem in physics. It will be S3P8, the 8th problem in physics in the 3rd season, and the name of the corresponding episode in which I will present my solution will be Twice Telescoping Rotating Antenna. And this is, again, the regulars of this channel already know this is my romantic take on a much more technical problem. But imagine that we have a telescopic antenna that, starting from certain ground level, let's say, begins rising in the strictly vertical direction, perpendicular to the base. And at this point, we have our origin, let's say O. So it begins rising vertically like this. So this is one telescopic direction, and then perpendicular to this rising antenna, there is another antenna that grows in this direction. So for example, at certain moment of time, or let's say initially our antenna was like this. This was this situation at moment 0. Then at some point the antenna rose up a little, and then vertically, and then perpendicularly to it another antenna came out that way in this direction. Then sometime later another ascent and another extension like this, and another ascent and another extension. So this is why the name of this episode will be Twice Telescopic. Plus, the whole thing, as this process unfolds, rotates in the horizontal plane with the constant angular velocity, let's say omega 0. And the thing that you need to know is that, let's say somehow we connect at any instance of time the point that sits on the perpendicular arm of our antenna, this point, and this point. If we connect this point with the origin, then the speed with which this point moves with respect to the origin, in other words, in this direction, is proportional to the distance. So in other words, this velocity is proportional to the distance from the origin to that point P. And the objective is try to figure out on your own. Again, I will present my solution, but you should try to do it on your own. Again, we continue studying the kinematics. There are no forces. This is just beautiful, clean, pure mathematics in some sense. So try to figure out two things. First, try to figure out which surface, as a hint, surface of revolution, evidently, because the whole thing is rotating, will the point at the edge of the perpendicular arm, telescopic arm, will trace or hug, if you will. That's number one. Number two, deduce the shape of the trajectory. In other words, write down the expressions for the coordinate x, y, and z in terms of the given material omega 0, and let's say proportionality constant k. See if you can do it on your own. And this is it for this episode. Thank you very much for your time. Thank you for watching. I will see you in the next episode, in which I will present my solution of the physics problem. S3P8.